Hello and welcome to this first video of the vectors unit. In this video I'm going to be introducing vector notation because vectors is a branch of mathematics that you may not be familiar with previously, and it's got its own set of mathematical notation that you need to learn before applying it and learning the arithmetic associated with vectors. So the unit outline of this video specifically is we will be looking at examples of vectors. Displacement and velocity are examples of vectors where speed and distance and speed respectively are examples of scalars. And the thing that differentiates a vector from a scalar is that it has both magnitude and direction, whereas scalars only have magnitude. And so this might be something that you've been introduced to already in physics. You do deal with vectors in the form of rectilinear motion, that unit in physics. In Math Specialist, you deal with vectors in a more Cartesian format in terms of coordinates in a Cartesian plane. Anyway, so you can also look at scalar multiples of vectors. That's something we're going to be going over. You can multiply a vector by a scalar in order to change its magnitude or also change its direction. And we'll look at examples of where that's the case. Then we'll also have a look at vector sums and vector subtractions by using something called the triangle rule or the head to tail rule and the parallelogram rule. So those are the triangle rule and the parallelogram rule are two ways of representing vector arithmetic, basic vector arithmetic. So in year 11 you deal with vectors in 2 dimensions, and in year 12 you extend that to 3 dimensions just to give a bit of foresight to what you might deal with in the future. So let's get straight into this video.
Okay, so the first thing I'm going to do is define what a vector is. And so what a vector is it's comprised of 2 components, these being magnitude and direction. So as an example, we might travel 5 meters and our direction in this case would be north. So this is our magnitude and this is our direction. Now vectors are importantly distinguished from something we call scalars by direction. Okay, so a scalar only has a magnitude. So in this case, for example, it might be 5 meters, whereas vectors have a direction associated with them as well. So in this case, 5 meters, in this case, is a magnitude, and so 5 meters is a scalar. And the way that we label this, denote this, is distance as a scalar. And the vector equivalent of distance is displacement, which is a vector quantity because it is directional. Okay? Another example might be 5 meters per second traveling south. Okay? In this case, this is speed, the scalar speed, whereas 5 meters in a southerly direction is referred to as velocity. So where vectors are directed, scalars only have a magnitude associated with them. And you might have already been introduced to this in physics. Another example of another vector is, for example, force. You always exert a force in a specific direction. You might also deal with acceleration. Acceleration is by definition a vector because you accelerate in a specific direction. Okay? So velocity, displacement, force, and acceleration are all examples of vectors. Where speed and distance are the scalar counterparts of velocity and displacement respectively. So we've also had a look at defining and using the magnitude and direction of a vector. Okay. In this next section, I'm going to deal with scalar multiples of vectors. So if I have a vector here, and this is a vector going in a specific direction, and it has an associated magnitude that is equivalent to the length of that arrow. And so here I have a magnitude, and let's say I label this vector v, then my magnitude is equivalent to the modulus of v. Okay, and so this is referred to as the modulus. It has the same symbol as absolute value. Essentially what this tells you is the magnitude of the vector. And if I'm looking at it in terms of a Cartesian plane, and I have my vector here like this, and I have my vector v, I can also denote my direction of my vector according to the Cartesian coordinates that vector makes with the x and the y plane. Alternatively, I can refer to it in terms of the angle that the vector makes with the positive x-axis. Okay? So I have my vector v here. Now, if I have a vector v, I can also consider a vector that is twice the length of the vector v. Okay? This vector that is twice the length of the vector v can be written as 2 times the vector v. And here, 2 is my scalar multiple. The vector 2v has the same direction, okay, and double the magnitude. This is the main difference. So the magnitude is equal to 2 times the magnitude of the initial vector. Okay, we can also deal with half of the length. In this case, this is 1/2 v, and this will have the same direction and half the magnitude. Okay? Now, if I have my vector v as well, and I have my v going in this direction, I can also consider a vector going in the opposite direction. I denote this vector as negative v. If my scalar multiple is negative, this implies that my vector will go in the opposite direction to the initial vector. Okay? If I have v and I have negative 2v, that will be a vector, negative 2v, that will be a vector with twice the magnitude of my initial vector and the opposite direction. So negative scalar multiples cause the direction to flip, whereas the coefficient, the value, the magnitude of the coefficient, in this case 2, is going to change the magnitude of the vector itself. So now that I've introduced scalar multiples and opposite direction negative scalar multiples, we can look at both vector addition and vector subtraction. If I have a vector A here, and I have a vector B here, so let's say A is my velocity of my plane by itself, and B is the velocity of the wind. Let's say I want to find the cumulative velocity of my plane. The plane's velocity will be acting in this direction, but the wind will be buffeting it in this direction. Okay? So if I want to find my vector addition, that is A plus B, then I need to add them head to tail. And notice as well, something I haven't pointed out yet, is that I'm using these symbols here to indicate that they are vectors. This symbol is known as a tilde, and it's how we denote vectors and differentiate them from scalars, distinguish them from scalars. So if A is a scalar, then A with a tilde is a vector. Vector, whereas this is simply a scalar. Okay? In textbooks, you generally see vectors written in bold, but when you're handwriting, obviously you can't write in bold, so instead you use this symbol of a tilde. And this is a really important notational characteristic of vectors, and you have to indicate them in every single question whenever you're dealing with vectors, otherwise you will lose marks. So keep that in mind. Back to A plus B. If I want to find A plus B, what I do is I add the two vectors head to tail, A and B. The resultant vector that connects the tail of A to the head of B is known as the resultant, and in this case it is equal to A plus B. And as you can see here, this is a triangle. And so this is known as the triangle rule for the sum of two vectors. I can also write and invert my vectors like this with B and A. All I've done is I've moved those vectors around. Here I have my vector B, here I have my vector A. B plus A is equivalent to A plus B due to the law of commutativity. And so this is equally valid. I should note as well that this is a parallelogram. And so this is referred to as the parallelogram rule of vector addition. Similarly, if I want to find A minus B, that is equivalent to A plus minus B. And so here I can see I have a scalar multiple of B. This is a scalar multiple, and importantly, the scalar multiple is negative. I have a negative scalar multiple, And so if I am trying to subtract the vector b from the vector a, what I'm really doing is I am adding the negative of vector b to vector a. So if in this case I have a in this direction, negative b would be going in this direction. And so this vector here, the resultant from the head to tail method, is referred to as a minus b. Okay, and so again, this is a triangle. And if I invert my vectors like this, I have my negative b, I have my a up in this direction. Then this forms, as before in vector addition, a parallelogram. Okay. It's badly drawn parallelogram, but there's the triangle, as you can see. There's also a triangle, and cumulatively they form an entire parallelogram. Okay, and so those are the triangle and parallelogram rules to find the sum and difference of vectors. This is the geometric interpretation. So this is importantly the geometric interpretation of vector addition and vector subtraction. So in the next video that I'm going to release shortly, I go over sort of the arithmetic or algebraic representation of vector addition and vector subtraction, where I introduce Cartesian coordinates in the component form of vectors. But for this video, that's all, and I will see you in the next one. Thank you.